Hello everyone. So first of all, I want to thank you, Emertxe, for making me being a part of this fantastic internship of making EV ADAS system virtually, and I've learned too many things I can't say. So let's first go through the requirements of the project. So this is the index, requirement and scope, system architecture, vehicle state machine, code walkthrough, simulation toolchain, result and acceptance. Okay. So purpose and scope. First is real-time EV sensing. Secondly is its ADAS safety, vehicle state machine, telemetry streaming, alarm acceleration, fault management. So functional requirements are read accelerator, brake pedal, ADC input at 100 Hz, compute vehicle speed via physics-based inertia model, estimate SOC. SOC is what state of charge, deducting based on power draw over time, estimate remaining range from SOC, support eco-normal sport mode, and it is from EV controller. Then coming to ADAS engine, we are triggering all three HC SR04 sensor in every 100 millisecond, and then we'll get the eco. Then time to collision TTC, warning when distance is less than 50 centimeter, and time to collision goes down from 3 seconds. Issue critical when the distance between the front HCSR 04 centimeter is less than 20 centimeter, and time to collision remains 1.5 seconds. Detect blind spot when side distance is less than 30 centimeter. Activate parking assist mode when speed is less than 10 km/h. Okay. Next, the functional requirements, fault and telemetry. The requirements are, so the high priority are transition to fault on motor overheat. When the motor get overheat above 90 degrees Celsius and SOC state of charge become less than 2%, we get fault. And then UART and telemetry, we have to transmit data from the PICSimLab virtual IO to the Python dashboard. There, for that we have used VSP, and that's it. System architecture, first is sensing, that's next we have perception, next is transport, next is application. Application is what? Python dashboard, which we have used, where we have used matplotlib library. And then in transport we the baud rate we have used is 115,200 bits per second. And that's it. For sensing, we have used 3 ultrasonic sensors, one for front, one for left, one for right, which is the model number is HCSR04. Now understanding vehicle state machine. This is the parked system, parked ready driving regeneration. In regeneration, whenever the system or we can say car use braking, that regenerative, that unused power, the heat generated is then go to charging system. And then we have, okay, we can understand the timers here. We have initiated 2 timers, TIM1 and TIM3. The why we have used timer, what timer actually does, it separates the code for and the checking system. If we have used code, we have to constantly check that that process has happened or not. But in timer, it callbacks the whole program, that every 10 millisecond and every 100 millisecond that, oh, see, this has happened. Okay, so it separates the interruption part from code to the timer. It make it independent, and it reduces the complexity of code and make it much faster. And during the internship we have learned how to program timers in STM32 IDE. Then code walkthrough, EV control.c, EV physics model. Okay, you can see here what are the flow of the code. Okay, I'll put it here for some time so you can see functions we have used, which are really key functions, are EV underscore init, EV underscore read, EDC, EV underscore update, EV underscore set drive mode. Okay, now for ADAS.c, in ADAS.c we are primarily calculating time to collision by reading data constantly from SCSR04 sensor in every 100 milliseconds. Now for faults.c and UART-shell.c, safety and net control, what the fault does is whenever the motor temperature goes very high, the yellow light we will be seeing in the demo part will get lit, and it shows fault. And whenever SOC, state of charge, goes less than 2%, then also yellow light get lit. You can see it in the dashboard part. Whenever there is a collision situation, then also we'll get the yellow light lit up, and we can see it in dashboard. Okay, now for the ultrasonic.c, so how ultrasonic works I'll quickly explain. It generate sound waves from the trigger, and for 10 microsecond will make trigger high. It means the sound is producing for 10 microsecond, and after that from the echo side will receive that, and between that time, as we know the sound speed from, and when that we received from echo, we count time from transmitting and receiving, and then what we do is we calculate the distance as we know the speed of sound. Okay, now software use, which is very important. I think we have used STM32 Cube IDE, which is the main thing. We have coded everything in STM32 Cube IDE, and for simulation we have used PICSimLab, and then we have used VSP, virtual serial port emulator. What it does is it connects internally two ports of the desktop. I'll explain it further when we see in demo. And then we have used Python for the dashboard. We'll see the code further. See the acceptance criteria. You can see both EV and ADAS UART packets within 10 seconds of power, false state entry in loop cycle. Okay, you can see here. So this is the presentation ending. I really want to thank Emertxe, and now we can see the demo part. Now we can go through the demo, but before going to demo, I think we must see all the things we have done throughout the internship. So first I'll show you the code part in STM Cube IDE. Okay, so here you can see our main C file. It is around, I think, 585 line of code. So in here you can see in EV dash in core we have includes have all the header files, adas.h, common.h, evcontrol.h, fault.h, main.h, UART shell.h, ultrasonic.h. Okay. And source, we have all the main file in C language. It is .c, evcontrol.c, fault.c, main.c, UART shell.c, ultrasonic.c. Okay. I think we must look the IOC file once, so we can understand what GPU IO pins we have used and what timer settings we have. It's taking a bit. Will you open it? Okay. See, we have used all these GPIOs, and clock configuration looks like this. Okay. I think we are done with the IDE. We can look into the setup first. Oh, I think motor temperature is increased, that's why it's showing yellow. Okay, down. See, we have virtual terminal, potentiometer setup to simulate situations, a 4 LED system in which red shows collision, blue is for left blind spot, green is for right blind spot, yellow is for fault situations. We have 3 ultrasonic sensors which are HCSR04, which are used to detect distance between car and the obstacle. We have 3, front, left, right. Okay. Now I think we must see the VSP thing. So VSP is a virtual serial port emulator. What we have done is we have connected COM18 to COM19 internally in my desktop, and what then we have done is we have connected the PICSimLab to COM18. You can see here, and what PICSimLab is connected to to Python dashboard. How we have done is we have done it through the command prompt. You can see the last line, it is connected on COM19. Okay, and we can quickly see the dashboard code also. This looks like this. Okay. Now we can go through the demo. Okay, you can see battery percentages are at 85.8. To show it's working, what we'll do is we'll simulate 2 things. We'll make motor temperature go drastically up. So first we'll do that. So what we will do, this PA3 is motor temperature, we'll increase it. Okay, you can see the yellow light got lit, which means it's a fault situation. Here you can see motor temperature 107.6 degrees Celsius, increased drastically from the previous condition. Now what we'll do, we'll just normalize the situation first. Normalize motor temperature. Oh, we have SOC, sorry. Normalize motor temperature. Okay, and what we'll do, we'll decrease the front obstacle distance. You can see red light and yellow light lit. Red light is for front collision, yellow is for fault, and you can see this in the dashboard. See, it's blinking. It means it is about to collide. Okay, TTC 0.01 second. At 0.01 second it will collide. Okay, I think we are done now.